And we're back. So I've just taken a slice out of the particle model theory that we learned about in Year 8 Science. I do have a video on this. I'll give you a link in the description below. If not, it should appear somewhere on the screen right now. But for air, as you know, is a gas, and it's made of particles or molecules which are evenly distributed inside the confines of its container, randomly and really spread apart. So there's empty vacancies between the particles that they could move into. This makes air compressible, meaning that if I were to bring in the walls of the container a little bit, there are places for each of these individual particles that could move into to accommodate that change in volume of that container. I want to draw your attention now to the fact that sound waves are made from vibrations. So if you've got something vibrating, you are creating sound. Now, you may not always be able to hear it, but almost everything you can think of has something to do with something vibrating. So let's go to something quite typical. So you obviously know that instruments, musical instruments, they all have some aspect which vibrates. For example, a guitar has strings which vibrate. A violin also has strings, and cellos and all those sort of string instruments. You've got woodwind instruments which have a little piece of wood or something, a reed I think it's called, in the mouthpiece, so that as you blow air over the reed in the mouthpiece, it vibrates and creates a sound which gets amplified down the length of its, the chamber. You've got drums, so every time somebody hits the drumstick on the drum pad, you've got a skin over the drum which vibrates and creates sound waves. Cymbals are behaving the same way. If you whack the cymbal, it starts to warp and vibrate. Even your own voice. If you have seen those really disgusting videos where somebody's taken a camera and put it down their throat, and you can see when they're singing, they've got little vocal folds where they press together, or they loosen up and they vibrate to create the different sounds and the different frequencies that the human voice is able to do. So vibrations are making sound. That's what a sound comes from. So why have I brought up these particle diagrams? Well, you have to work with me here. This is a really terrible drawing of a speaker. So that could be out of an amplifier. If you've got like a computer desk and you've got stereo speakers, even headphones, the ones that even go inside your ears, if you were to break them open, you'll find little ones of these where effectively on the back, let me use a different color, you'll see something that resembles like a magnet. It's sort of like a circular shape. Let me draw that a bit better. So it's like a magnetic shaped tube on the back, and you'll see like the cone, or I think they've got technical names, but I don't know them. You got this sort of framework which may have like metal parts to give it its frame, and then the other surface on this side, it tends to be made out of something that I think resembles a lot like cardboard, very, very thin paper like cardboard, and this is the diaphragm, and it vibrates back and forth, back and forth. If you've seen people who are really enthusiastic about souping up their cars and how they've got a great sound system, some of them have subwoofers, those huge speakers that are very large in size. And if you have seen them up close on a video clip, you can see that the whole diaphragm itself just vibrates slow enough for our eyes to be able to see it. If not, there's definitely some videos out there where you go enter YouTube slow motion speaker cone or slow motion speaker, and you should see these pictures where the diaphragm of the speaker cone pulses in and out, in and out, in and out. Now that we've got the basic concept behind a speaker, let's bring it to the diagram I've got here. So the magnet gets turned on with electricity, and that pulls the cone in. As it pulls the cone in, it creates a bit of a vacuum space right here in front. So there's less particles here, right where the cone just sucked itself in, than the air particles that are a little bit further ahead. So we get what we call the rarefactions. If you can remember in the previous clip there, where it's the places where there's relatively few particles in that space. Then power gets turned off to the magnet, which reverse perhaps, and it forces the speaker cone back out again. So you can imagine it sucks, makes a vacuum, and then it gets pushed forward. Boom! It now is cramming all these. Can you see these little particles here? It's cramming them all together. So the particles that were in front of the cone haven't had a chance to move out the way yet because it just slammed in very quickly. So now we've got a region right here in that middle, which has forced all the particles in a closer together. That is where we get our compressions. So I'm just going to cheat here and draw more particles in to represent those particles that were inside the cone that have just forced forwards. So now we've got a compression happening here. Those particles don't like that. And as you know from the particle theory, these are all bouncing around and having some energy moving around. So if you give them a moment, they are going to spread themselves out. As they spread out, they're going to spread out this way, and also this way too. But we're just going to focus on these two directions. So these particles are going to spread out in these two directions. So these ones here move back and fill in that space that used to be in front of the cone. These particles here are going to move this way, and they're going to slam into the region of space with these particles. So we'll start to get another compression happening here with a space between which has relatively few particles. So we create a rarefaction. And then guess what happens? The same thing's going to happen to these guys, where they're all bunched together. They're going to force themselves to spread out in both directions. So these ones here are going to slam into those particles here and create a more densely packed region of air particles. And it's also going to slam in this way to slam into those particles to make another compression. And it's going to do this back and forth as it radiates away from the speaker cone. Our ears detect these vibrations of compressions and rarefactions with our eardrums. It's almost like a receiving speaker cone. So if you can almost imagine another speaker cone right here, which represents our ear. This skin here from the eardrum can receive the compressions, which makes it push back. And then as those particles spread out again, the eardrum can stretch back out to its normal shape. And so as it picks up these sort of compressions and rarefactions, your eardrum can send that off, amplify it, and then your brain can interpret that as a sound that you can recognize. We'll cut the video from there. The next video, we're going to talk about some of the features of sound waves, some of the terminology we use to describe how sound waves are.